This is part 3 of the lecture on Copernicus, and it covers the second half of Copernicus's math, determining the distance that each planet is from the sun. Now, when Copernicus does this in the 16th century, he does not do so in terms of miles or kilometers. That, however, comes a little bit later on. Instead, Copernicus defines a term for us, what is called an astronomical unit. An astronomical unit, by definition, is the distance from the Earth to the sun. That's simply referred to as 1 AU. And we then determine the distance that each planet is from the sun in terms of astronomical units. Okay, so first of all, let me put it here on the board for you. 1 astronomical unit, what is called an AU, is the distance from the Earth to the sun. Okay, finding the distance that each planet is from the sun in terms of astronomical units involves just a little bit of right triangle trigonometry. For inferior planets, it's literally just one step. It's a little bit more complicated for superior planets, but first of all, for inferior planets. Okay, in the case of Mercury or Venus, what you do is you observe the planet at greatest elongation. That then gives you the following diagram. Once again, this is one of the important planetary configurations from one of my earlier screencasts. Okay, so here's the orbit of the Earth about the sun. Here's the orbit of the planet like so. Let's say that right here is the sun. Okay, let's go ahead and position the Earth right here. Okay, and then greatest elongation is defined in the following way. It's the greatest angular displacement that the planet is from the sun as seen from the Earth. So imagine looking at the sun like so from the position of the Earth, and then you look at the position of the planet in the sky. When you see this angle that I'm forming right here at its greatest value, that is what is referred to as greatest elongation. This then gives us a right triangle, which looks like this. Okay, let me kind of clean up the diagram here a little bit. Like so. And then I'm going to go ahead and construct my right triangle like this. Like so. Right here is the right angle, and then right here is the planet at greatest elongation. So at greatest elongation, this angle here is the largest angle that it's going to be for this planet. And when you do have greatest elongation, this line that I've drawn right here is tangent to the orbital circle here associated with the planet. This then gives us right here a right angle. Okay, let's go ahead and call this angle here theta. And then we have the following on this diagram. The distance from the Earth to the sun is 1 astronomical unit. And then the distance from the planet to the sun is our unknown. Let's just refer to that as x. Notice that if you just use a little bit of sine of theta, which is opposite over hypotenuse, just cross multiply and solve for x, and that then gives you the following. 1 AU multiplied by the sine of the greatest elongation angle then gives you the value of x, the distance that the planet is from the sun. Now, how could you easily observe greatest elongation? It's actually really easy to see, particularly in the case of Venus. The easiest way to see greatest elongation is to imagine the following. Imagine that you're standing on the surface of the Earth and you look at the sun on the horizon at sunset. So let's say that the sun is right there on the horizon in this direction like so. And then you look at the planet in the sky like this. Notice that I'm forming an angle here with my arm like so from the sun to the planet. When I do, I'm forming the elongation angle. When it's at its greatest value, that's then when you obtain this diagram here. So observing greatest elongation is actually easy to do, and this then allows you to calculate the distance the planet is from the sun. So Copernicus does this with Mercury and Venus, and he arrives at values that are pretty close to their currently accepted values. Okay, for superior planets, it's once again just a right triangle to determine the distance that each planet is from the sun, but it does involve a couple of extra steps. You need to know something about the planet ahead of time. You need to know its sidereal period P from the previous portion of this lecture. Okay, let me get to the description here. Okay, so now this is for superior planets. Okay, what you do first is you observe the planet at opposition. So recall what opposition looks like from earlier. Okay, so now here's the orbit of the planet about the sun. Here's the orbit of the Earth. And then right here we'll say is the sun. Okay, right here like so. Here's the planet. Here's the Earth. And then this configuration, remember, is opposition. Okay, opposition is actually really easy to see in the sky. Think of it this way. Let's say that the planet is in opposition, and then when it is, let's say that you happen to be observing at sunset. So then therefore the sun is on the horizon, say, in this direction to the west. If the planet is in opposition, where is it in the sky at sunset? Well, notice that the planet is on the opposite side of the sky as the sun, as seen from the Earth. So then therefore, if the sun is setting on the western horizon, the planet in opposition will be rising on the eastern horizon. So when a planet is at opposition, it rises at sunset. So knowing when opposition occurs is easy for that reason. And now what you do is you start a clock, and you then time how long it takes for the planets to go from this configuration, opposition, to quadrature. Quadrature looks like this. So the Earth is closer to the sun than the planet is, so it moves faster in its orbit, and then therefore quadrature looks like so. Right here is a right angle that is formed between the planet, the Earth, and the sun at quadrature. So let's say that looks like this, like so. So here's the planet at quadrature. Here's the Earth when that occurs, and we then form a right triangle on this diagram like so. Like this. So right here, once again, is the Earth like so. A right angle is formed between the planet, the Earth, and the sun when the planet is at quadrature. Once again, I described this in my screencast called Important Planetary Configurations. Okay, then you stop your clock when that happens. Okay, now how could you easily observe quadrature? Well, take a look at this diagram, and once again, let's assume that you're observing the planet as at sunset. So you're looking in this direction like so towards the horizon, and there's the setting sun. If a right angle is formed here between the sun, the Earth, and the planet when the planet is at quadrature, where is it in the sky? It's straight up. It's at the zenith. Technically speaking, it's on the meridian, but close enough. Just think of it as being straight up. So actually seeing quadrature in the sky is easy for that reason, because if you observe the sun at sunset, you would look straight up like so, and you would then see the planet at quadrature. Okay, now let's just look at the right triangle itself. What's what on the right triangle? Okay, let's call this angle here theta, like so. The distance from the sun to the Earth is 1 AU, and then it's the hypotenuse of this triangle here that's the unknown. That's the distance from the planet to the sun, like so. Let's refer to that as x. In this case, using a little bit of right triangle trigonometry, we would use cosine. So notice that cosine of theta, which is equal to the adjacent side divided by the hypotenuse, is equal to 1 over x. So if you now just cross multiply a little bit and then solve for x, x is equal to 1 over the cosine of the angle. So if you can somehow measure the angle theta here on this diagram, you can then just simply plug it into here and determine the value of x, the distance that the planet is from the sun, once again in terms of astronomical units. The trick, however, the extra steps, if you will, is how do you measure the angle theta? Okay, here's how Copernicus does so. First of all, take a look at the Earth on this diagram. On this diagram, the Earth moves from here to here in this time between opposition and quadrature. It moves through on this diagram a large angle. That angle, let me use a different color here, by the way. I'm going to use green, for example. That angle is right here, like so, in green. That large angle there I'm going to refer to as alpha, like so. Okay, now here's then how you can determine this angle alpha. It involves a proportion. For example, the Earth moves through the angle alpha on the diagram in the time necessary between opposition and quadrature. Time from opposition to quadrature. This is then equal as a proportion to the following. It takes the Earth 1 year to go 360 degrees on its orbital circle. So 360 degrees corresponds to 1 year. You would then just cross multiply and find the angle alpha. In doing so, by the way, this time here in the denominator of the expression would have to be written in terms of years. Okay, now take a look at the planet. The planet just moves from here to here in the time between opposition and quadrature. It moves through this smaller green angle right here. Let's refer to that green angle there as beta. Here's where the planet's sidereal period becomes important. I'm going to once again set up here another proportion. Okay, the planet moves through that angle beta in, once again, the time between opposition and quadrature. This is then equal as a proportion to 360 degrees on the planet's orbital circle divided by the time necessary for the planet to orbit the sun. That's its orbital period, its sidereal period P. So this is why we need to know the sidereal period P ahead of time, such that we can then use this proportion here to find the angle beta. Okay, so now we have the angle alpha from earlier. We now have beta from this portion of the calculation. What's the last step? Well, just take a look at the diagram above. The angle theta in blue, you'll notice, is the difference between alpha and beta. Theta is equal to alpha minus beta. So you measure this time as I indicated earlier, you set up these two proportions, calculate the angles alpha and beta, and then subtract such like we then obtain the angle theta. Once you've obtained the angle theta, you then plug it into the expression, and that then gives you the value of x. So it's once again just some right triangle trig, but we have to do a couple of extra steps here in order to find the angle theta. So Copernicus then applies this, using the data that he had, to Mars, Jupiter, and Saturn, and he arrives at values of x, the distance that each planet is from the sun in terms of astronomical units. He arrives at values that are very close to our currently accepted values. So Copernicus gets the basic layout of the solar system correct. He correctly calculates the time necessary for each planet to go around the sun, and he also correctly calculates the distance that each planet is from the sun in terms of astronomical units. This concludes this lecture on Copernicus.